This mini-lesson presents an example of how to calculate the work done on an object by the forces acting on it when those forces are constant. First, however, let's briefly review the meaning of the word work in a physics context. In everyday language, the word work has various meanings that we understand well and use often. However, physicists have adopted this word to stand for a very specific, precisely defined quantity. It describes the effect of a force on an object as it undergoes a displacement. In particular, if the force vector F is constant, then when the object undergoes a displacement delta r, the work that force does on the object is defined to be the component of the force parallel to the displacement vector times the magnitude of the displacement vector. If the angle between the force vector F and the displacement vector delta r is called theta, then the component of F parallel to delta r is F cosine theta, so that the work is F times delta r times cosine theta. This combination of factors, the magnitude of two vectors and the cosine of the angle between them, is called the dot product of the two vectors. So we can write the work done by a constant force succinctly as the dot product between the force vector and the displacement vector, or W equals F vector dot delta R vector. If the force is non-constant, then we have to break up the path traveled by the object into many tiny intervals. We make the size of the intervals so small that the force is essentially constant over each interval. Then, the work done by the force as the object traverses one such tiny interval delta r is dW equals F dot dr. To get the work done by the force over the entire path, we just add up, or integrate, the work from all of the tiny intervals that make up the path. In other words, the work done by the force as the object goes along its path from point r sub I to point r sub f is W equals the integral along the path from r sub I to r sub f of F dot dr. Okay, let's do an example for the case of constant forces. The figure shows a plane diving to the ground and then climbing back upward. During each of these motions, the lift force F sub L acts perpendicular to the displacement S, which has the same magnitude of 1.7 kilometers in each case. The engines of the plane exert a thrust F sub T, which points in the direction of displacement and has the same magnitude during the dive and the climb. The plane weighs 5.9 times 10 to the fourth newtons. Assume no other forces are acting on the plane. Part A asks, is the total work done on the plane greater during the dive or during the climb? Part B, find the difference in total work done during the dive and the climb. We'll work on Part A first. Let's consider the work done by each of the three forces in turn. First, the thrust of the engines. Since F sub T is parallel to the displacement, S, for both the dive and the climb, the work done by this force is F sub T times S, the product of the magnitudes of the force and displacement vectors. Since the magnitudes F sub T and S are the same for the dive as they are for the climb, the work done by the plane's thrust is the same for both cases. Now let's consider the lift on the wings. Since F sub L is perpendicular to the displacement S, for both the dive and the climb, it does no work in either case, because it has no component parallel to the displacement. What about the work done by gravity? Well, during the dive, the weight vector F sub W has a component in the direction of motion. This means gravity does positive work during the dive. In contrast, during the climb, F sub w has a component opposite to the direction of motion. Therefore, gravity does negative work during the climb. The total work is found by adding up the work done by each individual force. Lift contributes nothing in either case, and thrust contributes the same amount in both cases. For the dive, gravity does positive work, adding to the total, whereas for the climb, gravity does negative work, subtracting from the total. Therefore, the total work done on the plane is greater for the dive than it is for the climb. Before leaving this part, let's express our analysis in mathematical form. Here is the equation for the total work done on the plane. Since the forces are all constant, the total work is the net force vector dotted into the displacement vector. Since the net force is the vector sum of all three forces, this becomes the quantity F sub L plus F sub T plus F sub W dotted into the S vector. Distributing the dot product over the sum gives F sub L dot S plus F sub T dot S plus F sub W dot S. From the definition of dot product, we obtain F sub L times S times cosine of 90 degrees plus F sub T times S times cosine of 0 degrees plus F sub W times S times cosine theta. The first term vanishes since cosine 90 degrees equals 0, and the second term is just F sub T times S since cosine of 0 degrees equals 1. So the total work done on the plane is F sub T times S plus F sub W times S times cosine theta, where theta is the angle between the weight vector, F sub W, and the displacement vector, S. Now let's use this expression for the total work to compute the difference in total work done during the dive and the climb. This may seem like an impossible task since we don't know the value of F sub T, the thrust force. But we will find that it drops out. The total work during the dive is F sub T times S plus F sub W times S times cosine of 75 degrees, while the total work during the climb is F sub T times S plus F sub W times S times cosine of 115 degrees. Notice that the term F sub T times S is common to both total work expressions. So when we subtract them to find the difference, this term drops out. The difference in total work done during the dive and the climb is W subtotal for the dive minus W subtotal for the climb, which equals F sub W times S times the quantity cosine of 75 degrees minus cosine of 115 degrees. The expression in parentheses evaluates to 0.6814. Plugging in numbers and evaluating, we find that 6.8 times 10 to the 7th joules more work is done on the airplane during its dive than during its climb.